Hi, I'm CDubs. I just recently graduated high school, and today we're going to be going over a Shapes of Curves review. So first, I'll just say there are a lot of rules that you need to know about shapes of curves and stuff like that, and this is a review of shapes of curves. So if you want to go back and learn shapes of curves and learn the rules that goes with them, then we have a lot of videos on that on this channel, so feel free to go and check those out before doing this review with me. And also, shapes of curves is both an A, B, and BC topic, so this is a good review for both APs if you're here to study for the AP exam. Now, before we get into the actual review itself, I just want to go over some things that are very important when we're talking about shapes of curves. So the first thing that is very important is that you need to know all of the rules that go with shapes of curves, and that's what we have right here. All of this increasing, decreasing, concave up, concave down. These are the rules that you need to basically have memorized in order to be able to do shapes of curves well. So get those down. And when you know the rules, then when you're looking at a question, you can immediately apply the rule, and then you can just know how to do the problems better. It'll help you with figuring out what you need to do first and how to solve the problem. And then second, you need to know how to draw sign charts correctly. And the best way to do that is always factoring as much as possible. So whether you were given the derivative and maybe it's not factored completely, then you need to factor some more. Or maybe if you are taking the derivative yourself, you just need to make sure that you factor as much as possible so that preferably you can get an x plus or minus a number. And that way you can find the points that you need for your sign charts. Now, some teachers do find this by plugging in numbers to see where the graph is positive or negative, but I don't do that way because when you plug in numbers, it's a lot easier to mess up. So this way that I'll show you, and there's a video on how to make sign charts. This is going to be an easier way and probably faster, and definitely a way that you are less likely to mess up in. So if you want to find the way that you can make sign charts without plugging in, then we have videos on that as well. Okay, so now I'm just going to quickly go over these rules, and all of these rules will apply in the video. So f is increasing when f prime is positive, and that f prime is greater than 0, I'll be using that a lot. And that just means f prime is positive. And then same with decreasing when f prime is negative. So whenever we see in a question that we want to find where something is increasing or decreasing, then we know that we need to find the derivative. And then for concave up and concave down, we have those are related to the second derivative. So anytime we see concave up or down, then we need to find the second derivative. And then rel min and rel max, these have to do with when f prime changes signs. So for the rel max, when f is positive, then goes to negative. And then for rel min, when f prime goes from negative to positive. And then f has inflection points where f double prime changes signs. So when it goes from positive to negative or from negative to positive. And so when we see inflection points, again, we want to take the second derivative. And always factor completely. It will help you a lot and make the problem a lot easier, and it's generally kind of necessary when you want to find where y is equal to 0 so that you can find the different points that you need and find where the graph is positive and negative. All right, so I think we can kind of start the problem. Okay, so number 1. So right now we see we have f prime, that's the derivative, and we want to know where f is increasing. So when we see increasing, that means we need the derivative, but we're already given the derivative. But the derivative doesn't look completely factored, so the first thing that we want to do is we want to fully, sorry about that, we want to fully factor the derivative out so that we can find the points that we need. So of course we see the bottom right here. The bottom looks like it needs to be factored out, the x squared minus 4. So we want to split that into x minus 2, x plus 2. But also something that might be harder to find is the 5 minus x is not completely factored because we want x plus or minus a number. We don't want a negative in front of the x. So we then factored that out, we took out a -1, and now we have the fully factored part. And that's when we can then continue on and draw our sign chart. So we're drawing the sign chart now. And also here, right before we draw the sign chart, a lot of times I forgot to write this first in the video, but we want to note that this sign chart is going to be a negative odd sign chart. We know it's negative because we have the negative out in front, and we know it's odd because we have an odd number of x's basically in the problem. So this would be 1, 2, and 3. So we know it's negative odd, and that will help us with making the sign chart. And there are videos on that if you need help with knowing how to draw sign charts. So we have the -2 from here, the +2 from here, the 5 from here. So we've drawn our sign chart. This is a negative odd sign chart. Basically, we normally, when there are 3, we want to start and make it like this. Oh, well, the camera's flipped, so you can't really tell. But since it's odd, we would normally start and we would go like this. But since it's negative, then we flip it and we go like this. And all of them you go through because there are no even numbers. So there would technically be 1 here, a 1 here, and a 1 here, and 1 is odd. So we know that the line goes through every time and it doesn't bounce. But if one of the numbers were even, like if it were x minus 2 squared, then it would bounce. So like this would go like this instead of going through. But anyway, so now we know that f is increasing on -infinity to -2 because f prime is positive up here, and positive means increasing. And then we also know that it's increasing from 2 to 5 because, again, it's positive up here. So, though it's not part of the question, to note that f would be decreasing from -2 to 2 and from 5 to infinity because there f prime is negative. There we go. And there's me writing it in after the fact because I forgot. All right. And then number 2. So here we want to find where f is decreasing. Now, since it's decreasing, we know that we need to find the derivative, and we want to find where the derivative is negative, where it is less than 0. So in this problem, we were given f, not f prime, which means we have to take the derivative first so that we can get the function that we need in this problem. So here's me taking the derivative. We've got power rule where we have the 3 moves down, the 3's cross out, and then we have a 2. Here, again, power rule, the 2 comes down, the 2's cancel out, we have 3x, and then 4, and that becomes 0. And then, again, we want to factor as much as possible, so this is factoring as much as possible. We first want to take out the negative, and then we factor here, and we have that is negative even, negative because of this, and even because there are 1, 2 x's. So we've got -4 from here, 1 from here, negative even. We know that we want to go draw a line like that. And there we go. And since we're looking for decreasing, we want to see where f prime is negative. So we know that it's negative here and here because it's below the line. And so f is decreasing on -infinity to -4 and 1 to infinity because f prime is less than 0, f prime is negative. All right. Oh, also to note in the other one, we would also call that an upside down parabola. Yeah. All right. So number 3, we're looking for a relative minimum. And now we know that when we're looking for a relative minimum, again, we need to have that derivative. So first, we're going to need to take the derivative so that we can find where f prime is positive and negative. And for relative minimums, we know that f has a relative minimum when f prime is going from negative to positive. So here we are, we're taking the derivative. So e to the negative 2x, that would stay the same, but we have to do chain rule. So there's the chain rule of the derivative of negative 2x is negative 2, and then we multiply it by that. And then we do it again here, where the derivative of x plus 3 is just 1, so we just have e to the negative 2x. And then here, again, we're factoring as much as possible. So first we're going to take out the negative e to the negative 2x, and we're taking out the negative so that this x will stay positive. So we take that out, and we have x plus 3, but the 2 is there, so 2x plus 6. And we have minus 1 from this because we took out a negative, so that becomes negative, and we have the 1 from in front of it. And that's where we have this, and then here we simplified that, so 2x plus 5. And here we can cross out the e to the negative 2x because e to any power is always positive. So e is always positive. Anytime you have e in a problem where you're looking for a relative minimum or anything like that, or f, where f is decreasing or increasing, you can cross out the e to whatever because it's always positive. But keep in mind that we are not crossing out the negative here. We're only crossing out the e. So our line is still going to be negative. And it's a slope line because the x is not being squared by anything. It's just 1x, so it's a slope line. So here we are. We have x is equal to negative 5/2 when we set this equal to 0. And it's a negative slope line because of the negative out in front here. And so then we know that f has a relative maximum. Oh, maximum? Ooh, it's supposed to be a minimum. Well, it seems that the problem was wrong. Sorry about that. I think it should be asking for a relative max because that's what this is. This is a rel max here because f prime is going from positive to negative, and if you know your rules, you know that that is a rel max. So that's a typo in the problem. So rel max at negative 5/2 because f prime goes from positive to negative, and that is the rule for rel max. So if it were rel min, then it would have to look like this. It would be going in the opposite direction. All right, number 4. So we are given f double prime in this problem, and it's asking where we have an inflection point. And we know that our rule for inflection point is where f double prime changes signs. So if we were just given f, then we would have to take the derivative twice. But since we're given f double prime already, that means we don't have to take any derivatives because it's already given us what we need. And if you can see here, just to make sure if they give you what you already need, you want to look at it and make sure it's fully factored out. And if it is fully factored, then you're good to go. And that's where we are in this problem. It's already fully factored, so we don't need to do anything to find these points here. But if it weren't fully factored, you would need to do that. So we have 0 from our x squared, we have a, we have b. And now we are going to draw our sign chart. And we're drawing the sign chart looking at these things. So we start on the bottom because it's positive in the front. We bounce here because it's squared. It's to an even power, which means it bounces. Here we're going through because it's to an odd power, which would be 1. And then we're bouncing here again because another even power. So f has an inflection point at x equals a because f double prime changes signs. So this is not an inflection point, and this is not an inflection point because it bounces. It has to cross the line to be able to be an inflection point. All right, we're done with the first page. Good job. All right, number 5. So here we are looking for concave down, and now my hand is covering it, which is great. But we're looking for concave down. And if you see here, sorry about my hand again, Since we see the words concave down, we know our rule for concave down is when f double prime is negative, so when it's less than 0. And since we need the double derivative of f, that means we're going to have to take the derivative twice. Immediately when you see concave down, you see that we're given f, we know that we're going to have to take the derivative twice. So we're going to start out with taking the first derivative. We're doing power rule, moving the 3 up here, moving the 2, c, then this becomes 0. And then here we are, we're going to take the derivative again because we need f double prime for concave down. Doing power rule again. Remember that a, b, c, and d are constants, so you treat them like numbers and not variables. And then we factored it up here. Sorry, my hand is covering it. Factored it here. And just to be clear, because it's kind of confusing with the different, with a and b, the constants, but we're again solving for 0, so we would subtract the b and then divide by 3a. So we have x equals negative b over 3a. So that's our point. And then we know because this is positive, we want to do a positive slope line. And that's how we have our sign chart right there. And we know that f is concave down when the second derivative is less than 0, when it's negative. So this is where it's negative. So we know that f is concave down for negative infinity to negative b over 3a. There you go. And there was me writing it in after the fact again because I forgot again. I have a bad memory. All right, number 6. Oh, and I didn't move the paper, but that's okay because we'll talk through it and you'll see it in a second. So for number 6, we're looking for a local minimum, and a local minimum is the same as a relative minimum. So anytime you see local or relative, those are the same thing. And we know that we are going to need to take the derivative because we know our rules on local minimums or relative minimums, where we have a relative minimum when f prime goes from negative to positive, or from less than 0 to greater than 0. So we have our f, and here the first step, we know that we need to take the derivative, but to make it easier to take the derivative, we're gonna just move the x up and add an x, put the exponent there. So I just turned the k over x to k times x to the negative 1 because they're the same thing, and it makes taking the derivative easier, so we can do power rule. So we just rewrote it here, and then doing power rule, or we have 1 plus move the negative down, subtract 1, so we have this. And then we need to factor it because this is not fully factored. We don't just want a number kind of like sitting here. We want to make sure we can factor it completely. So that's how we're going to do this. Here we turned it kind of back into this form where we have k over x squared. Again, this is the same thing as this. And then we want to make it a full fraction. So this one, we just make it x squared over x squared. And then we put them together here. So we're very close to fully factored. But we still have this, we have a square, and we still want to simplify it as much as possible. So even when we just have a constant like k, we want to make sure we fully factor it as much as possible. So if you got to do square roots, then you got to do square roots. So that right there is what we have fully factored. We know it's even because it's positive, and positive because we have an even number of x's, so 1, 2, 3, 4. So even positive. And here we are drawing the sign chart, so we're going to have negative square root of k, 0, and square root of k. And since we know it's even positive, we know we need to start up here, go through, because this number is odd, this is odd, the pretend 1 there. 0, we want to bounce because it's an even exponent, and then we go through again. And to find our local min, we know that f has a local min where the derivative goes from negative to positive, so we know it's negative here, positive here. So f has a local min at root k, negative to positive. There we go. Also, just to add some notes, here, negative root k would be a maximum because f prime is going from positive to negative, and 0 would not be a maximum or a minimum because it's not crossing the line, it's not going from positive to negative or negative to positive. It has to be changing signs. To be clear, the derivative has to be changing signs for it to be a local min or max. So when it bounces, it is not a min or max. All right, number 7. So we're looking for where the particle is farthest left. And whenever you see farthest left or farthest right, that means it's an absolute min or max. So in this case, because it's farthest left, left is the negative, we know that it's an abs min, an absolute minimum. If it were farthest right, then we would know that it is an absolute maximum. But since it's left, it's a minimum. So here, this is the position. It would be kind of like equivalent to f of x. Since we're looking for a max, or sorry, in this case, we're looking for a minimum, we know that we're going to need to take the derivative. So this is us taking the derivative and then factoring as much as possible because it's positive and we only have one t, it's a positive slope line. Sorry, I don't know if you can hear my laptop fanning, but it's fanning now. So if you hear that, that is my laptop fanning. So, just so you know, since we're looking for an absolute minimum, this is the alternative way. We're going to see in number 8 the normal way of doing it, where we draw a chart and we find it based on numbers. But in this case, since we're not given intervals, which we'll see in the next problem, we're going to have to do it this way, where we just draw the line and we have to write this specific sentence for it. Because we have to basically explain why this is the absolute minimum for the whole entire graph for the particle, since we're not given intervals. So we know right here that it's a minimum because it's going from negative to positive, because that is the definition, that's the rule we know, where a minimum, negative to positive. This is the sentence that you would write for the alternative way of finding an absolute minimum. So we say, because the derivative is less than 0 for this interval, and the derivative is greater than 0 for this interval, the particle is farthest left at t equals 4. So we're basically saying, since the derivative is negative for this part and positive for this part, then the particle is farthest left at t equals 4. And we're using 0 and not negative infinity because we're talking about a particle. And when we're talking about particles, we don't really use infinity. All right, number 8. So we're finding the absolute maximum. So again, we know that we're going to have to take the derivative, but we want to use these specific steps to make it easier and to make it less likely to mess up, because when we're using a chart, we have to plug into specific functions. So using these steps makes it more clear and just easier to follow when you're doing the problem. So we're locating our function. So the function would be g, because that's the question. So it's saying find the absolute maximum for g. So g is our locate. And for g, we were given this, and we were given f of x. So here I'm just writing it out. We're doing 3x times f of x, and here's f of x. And then again, what we're saying before, we're actually not fully factoring out this time. This time we wrote it out and we multiplied them so that when we take the derivative, it'll be easier. And that's what we're gonna have to do in this second step. So the second step is finding the critical points, and that means we're taking the derivative, we're setting it equal to 0, and we're finding those critical points so that we can use those when we are using our chart to find the absolute maximum value. So basically put it in the form where it is easiest to take the derivative. And then step 2, take the derivative. So we're setting the derivative equal to 0, and we're taking the derivative of what I wrote right here. Power rule, again. And then now we're factoring it so that we can find the critical points, so that we can find those numbers that we're putting in the chart. So this is factoring it. We took out a 9, factoring it here. And then we have our critical points are 1 and 3. So now step 3 is we're going to make our table. So in our table, we want to use the locate function. Always remember step 3, table, we use the locate function. So we're doing x and g of x because that's our function here. So in our table, we have to use the intervals that they give us. So the intervals that they gave us was -1 and 2, because that's what it's asking. And then we also want to use the numbers that we found in step 2, the critical points. And in this case, and in every case, always make sure that the critical points that you put into the table are within the interval that they give you in the problem. So since our interval is from -1 to 2, then we have to do everything inside of that. And if you remember, our critical points were 1 and 3. Since 3 is outside of that interval, we don't put it in the table. But 1 is inside of our table, inside of our interval. So we put 1 in the table. So we know here, we just look at the numbers once we made, well, okay. We have to plug in the numbers, of course. I kind of skipped that because it's something you would put into a calculator and it's not very fun to calculate. But of course, once you have these numbers, you would plug -1 into either this or this or this. Probably this one, but maybe this one. It doesn't matter. You would plug -1 in. We plugged in -1. We did the math. We got -48. We plug 1 in. We get 12. We plug 2 in. We get 6. So that's how you do your chart here. And then once you have those numbers, then all you have to do is find the smallest number. And in this case, the smallest number is -48. And here's me messing up a bunch because I just didn't know what I was doing. And I wrote the absmin instead of the absmax, which is what the question was. So we know, while I'm struggling to write it, I'll just say, we know that the function g has an absolute minimum at x equals -1 of -48. So the absolute minimum value is -48, and this absolute minimum is at x equals -1. But since the question is asking for an absolute maximum, I'll just say it verbally that we would have an absolute maximum of 12 at x equals -1 because 12 is the greatest number out of those. So there we go. There's our video. If you have any other questions about shapes of curves or any rules that you need to go over, we have videos on that on our channel. And we have all types of reviews for a number of other topics for A, B, and BC. So if there is any topic that you're struggling on and would like a video on, then chances are they are on our channel. So just go check that out. And there are a lot of videos there to help with different topics and also with shapes of curves and all of the rules and things that go along with shapes of curves. So feel free to go check out the other videos on the channel. So just to note that shapes of curves is an incredibly important topic for calculus, and it would be probably third following derivatives and integrals. So of course you need to know your derivatives and integrals, but you definitely need to also know shapes of curves. It's very important. But anyway, that's all I have for this video. So again, feel free to check out the other videos on this channel. Subscribe and like if you thought this was helpful, and see you next time.